Thank you. My name is Nakash, and I am presenting about an innovative study for the hydrogen liquefaction, exploiting the benefits of CO2 precooling. My professor is Professor Moonjong Lee. I am from Process Systems Design and Control Lab, Yangon University. The contents of my presentation is first I will introduce a brief introduction of hydrogen, about hydrogen liquefaction from transportation perspective, challenges in the hydrogen liquefaction improvement potential with respect to the challenges, and what are the improved process or the subject of this study, CO2 pre-cooled hydrogen liquefaction, process design and simulation, result of this process simulation and its comparison with previous conceptual and commercial processes, and at the end conclusions. First of all, hydrogen introduction. As you all know, hydrogen is an energy carrier, likewise electricity. So we have to produce this hydrogen. The hydrogen is typically produced from fossil fuel based, natural gas or coal. Mostly it is produced from natural gas, about 76%, and the second most production source is coal. Hydrogen liquefaction from the transportation perspective. So after production, hydrogen is being transported from its production source to this consumption site. So typically hydrogen transportation is done through liquefaction in the form of compressed hydrogen, or is converted into any other chemical like ammonia or methyl cyclohexane. Problem with hydrogen is it has a low energy content on volume basis, but it has a high energy content on mass basis. As we can see that at the end of this block, you can see this hydrogen, gaseous hydrogen has low energy content on volume basis, but on mass basis it has higher energy content. As if we compare about the methane, liquefied petroleum gas, this gasoline at the top of this is a high energy content on volume basis. If you talk about the methane, which is a conventional fuel, methane lies here in the middle of this on a volume basis and on the mass basis. Hydrogen liquefaction transportation. Hydrogen liquefaction transportation is usually recommended for about more than 1500 km. Why it is recommended for more than 100 km? Because it is a highly energy intensive process to convert gaseous hydrogen to liquid hydrogen. So that's why if we increase the distance of this transportation, it will be economical to transport hydrogen as a liquid hydrogen. Why it is energy intensive process? Because if we see this conversion and reconversion energy required, this is for hydrogen, gaseous hydrogen to liquid hydrogen is 25 to 35% based on the LHV of the process. If we see on the supply chain basis, this is the step for liquefaction of hydrogen. After production, we will liquefy hydrogen, then transport it, store it, or to the consumption side or end user. The challenges in hydrogen liquefaction, as I discussed in mentioned in previous slide, it is a highly energy intensive process. The commercial hydrogen liquefaction processes all around the world is usually this specific energy consumption lies between 12 to 15 kilowatt hours per kg. It is quite a high energy consumption. So if we compare on an ideal basis, like how much energy required ideally to convert gaseous hydrogen to liquefied hydrogen is this 3.27. So from 12 to 3.27 or 15 to 3.27 there is a large gap between this ideal basis or actual basis. This graph shows that high energy consumption, this from different studies, this from literature review, energy consumption high energy consumption shows that low energy efficiency. So this is a major challenge, is to decrease its energy consumption and increase the energy efficiency of hydrogen liquefaction process. So here we can see that another challenge in hydrogen liquefaction is ortho to para conversion. Ortho para is an isomers of hydrogen. At this is like ortho. First one is ortho hydrogen and para hydrogen. In para hydrogen, this spin of electrons is reversed, and ortho hydrogen, the spin is on the same side. At 25 degrees C, in the gaseous hydrogen state, the normal hydrogen exists as a 75% ortho and 25% para. So ortho is usually at a higher excited state. So when we liquefy hydrogen, ortho hydrogen exists as 1% and para hydrogen is 99%. So from 75% conversion to 1% conversion is an exothermic reaction. So it releases heat and it increases the energy load on the liquefaction process. So this graph shows that what is the conversion of para hydrogen from ambient state to liquid state. From 25 degrees C to this blue line, you can see the para hydrogen conversion. So we can see that at the liquid state, minus 253 degrees C, you can see 99.8 degrees C, 8% para at minus 253 degrees C. So if we have to convert, convert this ortho to para hydrogen during this liquefaction process to attain the equilibrium between ortho and para hydrogen. So as we have discussed for the two major challenges, one is energy intensive process and the second is ortho to para conversion. Ortho para conversion, we have to include reaction during this process of liquefying hydrogen. So the major problem with energy intensivity is because of large temperature difference between gaseous hydrogen and liquid hydrogen. Typically it is done through stepwise cooling. First we do precooling, then cooling, then liquefaction. The most common temperatures selected for precooling, cooling and liquefaction in the previous study is precooling is at minus 160 degrees C, cooling at minus 230, liquefaction at minus 252 degrees C. If you can see that the large temperature difference is in the pre-cooling section. So minus 160 degrees C at out and inlet as 25 degrees C. So this large temperature difference is the most energy intensive section, and because of this high energy intensive section, it has high energy destruction. So any improvement in this section will be worthwhile for the improving of this whole process, the liquefaction of hydrogen. In this graph, we can also see that which section is the most energy intensive section. So here is the temperature of hydrogen throughout in the pre-cooling section from 20 degrees C at the inlet and outlet minus 160 degrees C. Minus 160 is the outlet of hydrogen at pre-cooling section. So this high graph, so this graph is the approach temperature graph. In other words, it is the META value, minimum internal temperature approach value. The high, it should be this in the range of 3.138 degrees C, because 3 degrees C is the recommended delta T in the cryogenic heat exchanger. So if the value is high, it means that there is a high exergy destruction. So in the pre-cooling section, we can see that the approach temperature is 33.17 degrees C. So it has a quite high difference between 33 and 3.1, around 30 degrees C. We can also see that there is a large gap between this red line and blue line. Blue line is cold composite curve and the red line is hot composite curve. These graphs are drawn from the cryogenic heat exchanger profile, heat profile basically. So this profile shows that there is a large difference between hot streams and cold stream. Cold composite curve represents cold stream and hot composite curve represents hot stream. So there is a large gap, there is a large heat transfer delta T. So we have to decrease this gap. So this is the reason, that's why there is a high energy consumption in the precooling section. So what is how we can improve it? According to our main process, we have to divide this section. As we mentioned that because of large delta T, there is this energy consumption. So what we do is decrease this delta T. For example, if we divide this minus 160 degrees C into two halves, like minus 180, then from minus 180 to minus 160, we can have some energy saving potential. So question is what we do in the first section, minus from 25 degrees C to minus 180. There are several refrigerants which we can use this to, which are energy efficient refrigerants. The most commonly applied refrigerants are hydrocarbons, ethane, carbon dioxide. We can also use carbon dioxide in this range. If we compare the ethane and carbon dioxide, both have boiling points near to minus 180 degrees C. So we can use these two refrigerants in this first half of precooling cycle. And if we compare this ethane and carbon dioxide, keeping the design parameters same for the simulation, we can see that carbon dioxide has high specific refrigeration effect and have high coefficient of performance and figure of merit. So we can say that carbon dioxide is more efficient than ethane in this first precooling of hydrogen. So, in this, this is a basic flow diagram of designed process. In the first process, we have used a carbon dioxide cycle. Carbon dioxide is a pure refrigerant in this cycle is used. And in the second cycle, second precooling cycle, we have used conventional refrigerants, C1, C2, heavy hydrocarbons. And in this section is the cooling section, and this section is the liquefaction section. And these three reactors are installed as an ortho to para reactors to convert octohydrogen to parahydrogen. So to convert this octohydrogen to parahydrogen, we have used the equilibrium data, published equilibrium data from the literature. And from feed condition 75 to 25% hydrogen, 25 degrees C is stepwise liquefied. Here is the first precooling, this is cooling, this is liquefaction, and at the end we have liquefied hydrogen at minus 252 degrees C and with the para conversion of 98% at 1.3 bar pressure, the storage conditions of liquid hydrogen. So here are some preliminary results of this design process, with the comparison of commercial process and conceptual processes. Commercial processes so far are from Praxair, Linde, at Ingolstadt or at Leona. We can see that the high energy consumption, 12.5 to 15, 13 to 15, these are installed commercialized processes with the low efficiency. In our design process, the energy consumption is 7.62, which is comparatively very low from the commercial process, with high energy efficiency of 31.4%. If we compare with the conceptual processes, conceptual pre-cooled processes, many published in the literature is nitrogen pre-cooled. Mostly they have used nitrogen as a pre-cooling, pure refrigerant in the pre-cooling section. But we have divided the pre-cooling section into two halves. So we have successfully reduced the energy consumption of hydrogen liquefaction to 7.62 and 31.4, which you can see that they are relatively very low energy consumption as compared to the conceptual process and high energy efficiency. So conclusions, we can see that dividing the pre-cooling section is a very promising approach for increasing the energy efficiency of energy-intensive hydrogen liquefaction process. CO2 can be used as a pre-cooling refrigerant for high specific refrigeration effect, coefficient of performance, and figure of merit values when compared with ethane. So if we can see that this 7.62, it still quite high value as compared to the ideal case. Ideal case is 3.27. So we can further improve this section by dividing and in this improving this part by using propane or ammonia as a refrigerant, high boiling refrigerant, to further decrease this energy consumption and increase the energy efficiency of the process. This graph shows that the results of this process, energy consumption is 7.62 kilowatt hour per kg, and the energy efficiency is 31.4%. This coefficient of performance, figure of merit, and total annualized cost is also calculated. You can see that 24.2 is annualized cost, and the coefficient of performance is 0.31, and the figure of merit is also calculated. So we can use the CO2 as a precooling refrigerant, but there is one limitation of using CO2 as a refrigerant. And what is this limitation is CO2 is bound to freeze when used below triple point conditions. CO2 can be freezed at below the triple point conditions. Triple point condition is 5.1 bar and minus 78 degrees C. So what we do is we use this CO2 in this section above triple point. So the lowest pressure is above the triple point pressure of CO2. So we can mitigate this limitation, we can solve this limitation of CO2. Thank you. Do you have any question and answer?
Thank you for your explanation. Anyone has some questions? I have one question. How much amount of carbon dioxide should be used to operate your imaginary system?
Actually, the quantity of CO2, carbon dioxide, is variable. We have to optimize this quantity, this mass flow rate of CO2 to optimize this process, because we can adjust this process through optimization. So through optimization we can reduce the flow rate of CO2, and it depends on the pressures of the refrigeration cycle. If we are using CO2 on low pressure ratio, a high amount of CO2 is used. So if the pressure ratio is high, then low amount of CO2 can be used. So this is variable quantity, is not like fixed. But when the process is designed and optimized and running on the same condition, then the same flow rates is used throughout because it is a closed loop refrigeration cycle.